overlapping. Hey guys, in this one we're going to start talking about the wave behaviour of light. So hopefully this is a little bit of a recap from last year where we did a fair bit of stuff on light and on waves. So hopefully some of this is a little bit of a refresher. Obviously it's not all going to be. So to kick it off, we're going to talk about the production of electromagnetic waves. Now, we, as in society, do this using transmitting and receiving antennas. So a transmitting antenna is literally just a massive tall conductor. And hopefully from the field stuff, you can remember that if you make electrons move, you make an electric field move. Now, if you can make electrons oscillate by having an alternating current like this, what you'll have is electrons running up and down, up and down, up and down, up and down your massive long conductor. What this does is sends out an oscillating electric field. Now, every time you have a moving charge, remember you also have a magnetic field being generated. So these two things are the right-hand rule, are perpendicular to each other at all times. So if the plane of the electric field is in the plane of this board, then the plane of the magnetic field would be in the plane of like you to me, or me to the camera, me to the board. All right, so we're going to have this electric field oscillating up and down like this, and that's simply because we have a alternating current making electrons move up and down. Their fields come out as a big wave. Now, over here we have another antenna, so this is going to be our receiving antenna. So that's going to be our transmitting one. This is going to be our receiving one. So this receiving antenna now is just kind of sitting there in space, and it has this oscillating electric field coming past it. Now, when you have electric fields, they do work on electrons. They make electrons move. So A is EQ on them. So if we have an electric field, we're going to make an acceleration. So our charge is going to accelerate. Now, if our electric field is oscillating, the acceleration of this thing is going to oscillate. So we're going to have this particle move up, down, up, down, up, down, up, down. So this electric field comes past, and it's going to make electrons run up and down, up and down, up and down. And what we can do then is pick that up as an alternating current at the bottom of this antenna. So our antenna is going to transmit by putting a current in, and it's going to receive by receiving a current out. Now, obviously, the input here is going to be significantly bigger than this because you have your, transmitting antenna sending it out in 360 degrees, whereas you're receiving only one of those little bits and pieces. Now, it's important to note that if I was to get another antenna, and I put it like this, I'm also going to be making the electrons in this thing. I'm also going to make the electrons in this thing move up and down. Now, if I'm trying to receive it at the end here, and these things are moving up and down over here, they're not actually going to come out the end. So the orientation of my receiving antenna needs to be the same as the transmitting one. This is a handy thing in TV situations where channel 7, 9 and 10 broadcast around about 200 megahertz, I think it is, and they're all reasonably close bandwidths together. Now, if you throw in a country station like the GDS-BKN or Southern Cross or whatever the hell they call themselves now in Piri, and they oscillate vertically as well, you're going to have some signals overlapping, sort of interfere in the middle somewhere, and you'll get constructive and destructive interference. That stuff's coming in the next video. So the speed that these waves all travel out through space at is given by v equals f lambda. So v is obviously the speed. With light, we talk about, so the speed of light is the speed of the universe, I guess. It's the universal speed limit. So usually it's called c, that you'll see. So that's the speed of light. And that's 3 by 10 to the 8 meters per second, so it's really bloody quick. F is the frequency, measured in hertz, named after a German guy called Hertz. Wavelength, lambda is the wavelength, and obviously lengths are measured in meters. So you have this, how fast each wave is going depends on how many times it takes a step, multiplied by how big those steps are. All right, and In terms of light, electromagnetic radiation, it's 3 by 10 to the 8. In terms of sound, which we dealt with last year, it was about 330, give or take, meters per second. All right. Thank you.